In Chapter 6, we're going to talk about thermochemistry, or the chemistry as it pertains to heat. The transfer of heat is often a big driving factor in whether a chemical reaction occurs or not. So we need to make sure that we understand how energy plays a role in reactivity. Alright, recall from the first chapter when we talked about matter and energy that energy is the capacity to do work. And remember that work has a definite definition in terms of chemistry and physics. That is, work is equal to force times a displacement. Or you have to move something a distance in order to have done work. And the energy that we talk about comes in many different forms. There's radiant energy, which comes from the sun and the stars, and it's light, transmission of energy through air or through space without any medium. For example, light flows through outer space and comes and hits the Earth. There's also thermal energy. Thermal energy, heat, is associated with how fast molecules are moving, the kinetic energy of the tiny particles. Chemical energy is stored energy within the bonds. For example, sugar has stored energy. When we consume sugar, we break that sugar up into CO2 and water, and we use the energy to fuel our body. Nuclear energy is stored within the nucleus of the atom. That's where we have energy, electricity coming from the nuclear power plants. We split atoms apart into two different new atoms, and we capture that energy and turn it into electricity. And potential energy, this is specifically gravitational potential energy. So that by gravity is the energy based on the position of an object. For example, if you have a ball and you hold it a meter above the ground, it has energy. When you release it, it falls to the ground. Its energy that was stored, potential energy, is turned into kinetic energy, energy of motion. So all these different types of energy, really the big basic ones are potential and kinetic energy. Now, what we call heat is actually the transfer of thermal energy between two things at different temperatures. It is not energy. So temperature does not equal energy. Okay? It is the energy flow. It is a measure of the thermal energy, but it's not energy. So in order to measure our energy flow, we have to define a frame of reference. And in physics, a frame of reference is the way you view what you're wanting to study. So we have what we call the system. And the system is particularly the things that you want to study. So for us, chemical reactions. That is the system. Now, hopefully, we can study just the system. But the problem is, the systems may not be easy to study on their own. So we have here a bunch of different systems. These systems are going to be open systems, open, closed, and isolated. Now, in an open system, we can exchange both mass and energy. Things can leave our system, physically leave the system. Energy can move in and out of the system. So this is kind of like a bottle of water with the cap off. Now, if we want to close that system off so that we don't lose mass, so no mass loss, we can just stopper it up. The only thing that can transfer now is the heat energy. That is still able to move back and forth through the system and everything else. Now, what would be great is if we could isolate the system. It's much easier to study an isolated system, but guess what? There's no way to truly isolate a system. You can do pretty good, but you'll never be able to truly isolate the system. So, most of the time, what we are going to be working with are our closed systems. So we're going to be looking at energy changes. We're not going to be looking at a lot of mass change like with the water vapor leaving. So the closed system is what we're going to study most often. Now, if we're going to deal with that closed system, we know that we can exchange energy. So specifically, since this is thermochemistry, we're going to talk mostly about thermal energy. And we can define two different processes, an exothermic process and an endothermic process. An exothermic process is going to give off heat to the surroundings. Now, when we define our system as something that we want to study, just that bit that we want to study, then everything else in the rest of the universe is the surroundings. So, in an exothermic process, heat is given off to the surroundings from the system. So something like burning hydrogen and oxygen to get water. That is an exothermic process. Another exothermic process is the condensation of water vapor into water liquid. That also gives off energy. Now, an endothermic process is going to be the opposite of the exothermic process. Endothermic processes are going to be where the system absorbs heat from the surroundings. So, something like breaking apart mercury 2 oxide, or breaking or melting ice. Solid water goes to liquid water. It takes energy input in order for those processes to occur. So we can rough diagram these processes in terms of the energy content. You will see here that at the top, at higher energy, we have our hydrogen gas and our oxygen gas. When they react to form water, heat is given off by the system to the surroundings. And then our products are lower in energy than our reactants. So with an exothermic process, the energy of the products, or of our reactants, energy of the products is less than the energy of our reactants. In the case of an endothermic process, we have our products up in a higher energy and our reactants are lower in energy. So in this case, the energy of the products is greater than the energy of the reactants. That's because heat energy must be absorbed from the surroundings to the system. So that's how we get a higher energy product. So in thermochemistry, if we want to study all these changes, this is really what we call thermodynamics. It's dynamic because it's constantly changing, the change in energy. And we're going to talk about changes in heat and all the other types of energy. Now, in order to understand the thermodynamics, we have to make some definitions, and we have to be able to talk about how energy is stored. And in order to do that, we have to talk about the state function. Now, state function is something where the properties of the system are determined by the state, not how that state happened to occur. So here we have a case of gravitational potential energy. Both of our little hikers there are some distance h above the ground. Let's say they weigh exactly the same, so they have the same mass. They would have potential energy equaling their mass times the gravitational constant times the height. So that is their potential energy. Now, you can see that hiker 1 here took a fairly straightforward path. Hiker 2 took a very circuitous path. But they both have the same potential energy. Even though they took different paths, they still have the exact same potential energy. So here we have our energy, U. U final minus U initial equals the change in energy. So here's their final stop, here's where they start. So final minus initial. Things like pressure and volume and temperature are state functions because it doesn't matter how they got to that state. All that matters is where they start, where they stop. And because energy is a state function, we can define the first law of thermodynamics. And this says that energy cannot be created nor destroyed, but that it changes its form from one to another. What this really means is that if we have our system and our surroundings, the change in energy of our system plus the change in energy of our surroundings must equal 0. Or the change in energy of the system is opposite that of the change in energy of the surroundings. So that means that if the system loses energy, the surroundings gains energy. If the system gains energy, then the surroundings lose energy, which means that the energy of the universe is constant. So all the energy that was or ever will be is already here. Let that sink in. That's pretty darn important, that all the energy that ever was is already in the universe, just waiting to change forms. So with the combustion here of propane, what we actually see is one heck of an exothermic reaction. So what is given off by the system, our propane and our oxygen, can be absorbed by the surroundings. Say, a hamburger or a hot dog on your propane grill. So another way we can write this first law is if we take a look at the energy in terms of the signs. So we cannot measure internal energy very easily because it's the sum of a bunch of different energy modes of storage. But what we can do is we can measure changes in energy, so the change in the internal energy of a system. That is equal to the sum of the heat and the work. So the change in internal energy is heat plus work. And work can also be defined as negative P delta V if we have a constant external pressure and a gas expanding against that. So, the sign conventions here are as follows. If work is done by the system on the surroundings, then the sign is negative. If work is done on the system by the surroundings, then the sign is positive. So you can think about that. If you're pushing against something, you're doing work. That is work being done by the system on the surroundings. But let's say you're trying to push a spring down. You're doing work on the system and you're the surroundings. So energy out would be a negative. Energy in would be our positive. Similarly, if heat is absorbed by the system from the surroundings, the sign of heat is positive, and if it is given off an exothermic process, the sign will be negative. So let's talk about this work bit here. Work is equal to force times displacement. We've already talked about that. But work is also equal to negative P delta V. And the reason that that works is if P and V are there, that's actually pressure is our force over an area, and volume is just length times width times height, so it's really a length cubed. So when you multiply that together, you get force times displacement, so it's actually work. Now, work is not a state function. Work depends on how you get there. It's different than internal energy. Now, this is actually a misnomer. This is not work done on the system. This is work done by the system. Here we have our initial setup. Now, the gas is going to expand against a constant external pressure. So the change in volume here is going to be greater than 0. But that means that the negative P times delta V must be less than 0. So work done by the system is less than 0, or work on the system is less than 0. So that means that the sign of this system is a negative. You do not have to know how to derive all this, okay? Just know the sign conventions we just discussed. That is the easiest way to keep this straight. Similarly, you won't have to know how to derive enthalpy from the first law of thermodynamics, but suffice to say, we're going to show you something neat. So, if delta U is equal to Q plus W at constant pressure, then work is equal to negative P delta V. So delta U is equal to Q at a constant pressure plus negative P delta V. Or delta U is equal to Q at a constant pressure minus P delta V. So we're going to take QP and we're going to define that as H. Okay? So the delta H is equal to delta U plus P delta V. And if I substitute in delta H is equal to, well, delta U we know is Q plus W. So QP plus W plus P delta V, which is negative W, then really what we have is delta H is equal to QP, Q at a constant pressure. Or really, the heat is delta H. Now, delta H, the enthalpy, this guy is a state function. All that matters is where you start and where you end. So delta H is equal to the enthalpy of the products minus the enthalpy of the reactants. So final minus initial. That's all that matters, is where you start and where you stop. Now, remember, this is if things are done at a constant pressure. If things are not done at a constant pressure, if pressure changes, we have to adapt slightly. It's not all that bad, but just a little bit of adaptation and we can determine energy changes. Now, with this enthalpy change, if our products are higher in energy than our reactants, products higher than reactants, then delta H is greater than 0. That means energy is being absorbed. This is an endothermic process. Endo. If the energy of our products is less than that of our reactants, then delta H is less than 0. This is an exothermic process. So, the sign conventions for delta H: exothermic processes are negative, endothermic processes are positive. Now, in the following videos, we're going to use this concept of enthalpy to monitor chemical reactions and to help to explain how chemical reactions occur.